Welcome. Okay, so the title's on the screen in case you want to make sure you're in the right room. So let me start off by asking everyone, how many of you guys have ever looked at the assembly your compiler spit out? Great. How many of you felt like you understood it to at least some degree, any amount greater than 0 of understanding? Excellent. How many of you ever looked at the assembly and just felt, man, this assembly's crap? Okay, good. So about half. A couple of weeks ago, story time, I was flying with my son, without my wife. Not a good combination. And he was staring at some airplanes, and then he said to me, potty. So I picked him up and I ran through the airport, but I was too late, and everything just came out. It wasn't only pee, I'll say that. I was covered, he was covered. I took him to the bathroom. All of his clothing went in the garbage. I washed him in the bathtub. I ran back out with him naked in my arms. And I dressed him. So I'm not as quick to call assembly crap anymore once you've seen the real thing up close. So let's talk about what the talk is. The idea of the talk is to get a better feel for the assembly that's produced, not all the detailed instructions, but the overarching features, especially really critical things like inlining and branches, say. It's try to understand, this is very important, what optimizations can you expect a production-grade compiler to do for you? Which ones can it not do? And also to understand how the compiler is limited. There's some cases where the problem is not that the compiler is not smart enough, it's just that it's not possible for the compiler to know what it needs to know or do what you want it to do. What the talk is not is all these things. That is to say, I'm not giving a hardcore tutorial on assembly. I'm not qualified to do that. There's no benchmarks. I know it's almost heretical to not have benchmarks in a talk like this, but that's just not the focus of the talk. There's nothing about multi-threading. We're just going to be talking in the single-threaded universe. Multi-threading is a huge topic. And the same goes with link time optimization. It's just things that I'm not going to be covering. Okay, so why is it important to understand this? Well, you could just write and measure. This isn't very efficient, right? You could just randomly type some code, measure something, and then you could start making random changes and measure again. And you could just keep doing this, but this is a random walk. You're not going to get the fast code very quickly. So it's a lot better if your changes are motivated, at least if they're educated guesses, right? Measurement can be hard. If you're not the end user, you don't have a benchmark per se, right? You have your benchmark. It might be different from the user's benchmark. So it's not always good enough to say, well, this code path doesn't matter in my benchmarks. Maybe in your user's benchmark, it will matter. And finally, when you design code, it's not, people sometimes have this idealized notion like they're going to have this one 50-line function that accounts for 99% of the running time that they care about, and they're just going to optimize it at the end. It doesn't usually end up working that way, or it would be a lot easier if it did. If you guys went to Mark Ellen's talk on Tuesday, he said performance is hard to retrofit, right? And if you have no clue what the compiler is producing, then it's hard to design. And if you can't design it and you can't retrofit it, then then performance just becomes hard, right? Or harder. So what's my job? I work in high-frequency trading. I'm not on an infrastructural team. I'm actually on a trading team itself. So it's a very small team of people, just 6. And there's only maybe 4 people, say, that are proficient at C++. We have lots of responsibilities other than just purely, cranking out C++. So there's just not a lot of time to go around. I mean, there's been times when we said, hey, let's optimize this, and 6 months go by, and we just don't have a chance. We don't have time. So you need to write fast code quickly. You may not have all the time in the world to sit there, benchmark all the different cases. You need a good intuition about what is likely to be fast. Or at least some intuition, maybe not a good one. Okay, so why am I giving this talk? That's a good question. I'm not a compiler developer or expert or on the standard, but I do write a lot of code, and I look pretty carefully at the assembly that comes out, and I have a mental model that works reasonably well for me, at least to infer certain kind of conclusions. So, yeah. So I've said that the talk's not that exciting, and it's not about these things, and that I'm not super qualified. So the secret to a good talk is like the secret to a good marriage: lower expectations, right? I always tell my wife this. Okay, so let's motivate things with a more clear-cut example. So this is a real thing that came up in code review a few weeks ago. So someone was using a vector of int, and they were basically keeping like their own size, so they wouldn't have to call clear. Because the documentation for clear says, well, this is on, right? What does clear do? It destroys all the elements, right? So if you have a vector int, well, is it still going to be on? How many people think yes? How many people think no? How positive are you? 100%? So fewer hands. So we'll come back to this example later. Okay, next example. I mean, qsort, stdsort, they're such canonical examples in terms of both C versus C++, in terms of function pointers. So here's how I see the average C++ developer progressing. You're a beginner. You learn they're both n log n because they're both quick sorts in school. Done. Then you start to learn. You read Scott Myers. He says stdsort is faster because you get inlining. Great. That's pretty good, actually. But then you go to the next level, and I've had very experienced developers tell me, no, it'll be the same because the function pointer will get inlined. Modern compilers are smarter than that. And then you realize it depends. I mean, maybe they will, maybe they won't. And we'll also come back to that example. So here's another kind of weird example. So here's two calls to stdsort. They have the exact same behavior, right? I have a comparator, which is a function. In the first case, I pass the function directly. In the second case, I'm doing something kind of weird, right? I'm creating a lambda, and the lambda calls the function, right? What the heck's going on? Okay, so who thinks that 1 would be faster? Raise your hand. Okay, a few hands, not too many. Who thinks that they're the same? Who thinks that the second one's faster? Great, so I'll say that the same was more than half of the people, and some people said the second was faster, and almost no one said the first was faster. We'll come back to this too. I remember who put up their hand. Okay, so how can we resolve this? Well, we could run a benchmark, but you know what? If you think the assembly might be identical, it's actually a lot faster just to look at the assembly and diff it, and it's more reliable because measurements have noise, right? And there's also a lot of pitfalls. So you look at the assembly for one, you look at the assembly for the other, and then you start to see, well, is it exactly the same? And then if it's not, then you can benchmark them and think about which one's faster, right? So we're getting the kind of whether there's a difference or not straight from the machine itself. So we look deep inside our function. And when you look deep inside the function, you'll see a call to this intro sort loop. So intro sort is the hybrid loop that, hybrid sort that the standard sort uses. And deep inside its bowels, if you go through the assembly, you'll find this call R12. So R12 is a register, call is calling it. So there's an indirect jump, okay? And the only compiler and flag optimization, at least out of 01, 02, 03, in all cases except for GCC with 03, for every other compiler and optimization flag, if you have the lambda, it gets inlined. And the one with the function pointer does not. And you can benchmark this, and obviously you can always concoct an artificial benchmark, but generally speaking, the inline one will be faster in almost any benchmark. So the majority of people thought that it would be the same, right? But it's not. So when you add that lambda, in most cases, it will make things faster. So it just kind of shows the relationship between assembly and code is pretty tenuous, right? An extra function call in code actually made things faster. So in this case, the lambda was like negative cost, right? Pretty weird. Okay. So isn't this optimization easy? Well, no, not really. Depends how you look at it. Okay, so in order to make this all seem less weird, we're going to talk a little bit about some very basic tools to think about what an optimizer has to work with. And then we're going to come back to more examples, a lot more examples. Okay, who's seen the movie Training Day? It's like 10 years old now, I guess. Oh my God, everyone else get out. No, I'm just kidding. Okay, so the movie is about this naive cop that joins a unit with this corrupt but effective cop played by the ever wonderful Denzel Washington. And one of the refrains in the movie is he keeps telling the younger cop, it's not what you know, it's what you can prove. So the same thing is true about the compiler. Okay, you may think you know something. I'm only going to use the function this way. I'm only going to do that. The compiler doesn't care. The compiler will only do what it can prove is correct. So every optimization is like a proof, right? It has to prove that given what it knows, that all of the observable behavior is always the same in the original code and the optimized code, okay? So, you have to define observable. I'm not going to do that. I think Bryce has talked a bit about this. The C++ execution model, definitely should watch that talk, but we're not going to get into the details of observable, but it's at the very least common sense things, right? It's got to return the same value from the function, right, for legal inputs. Okay, so basic blocks, I'm not going to get, again, in very much detail here, but it's a basic concept that it's worth at least knowing the Wikipedia definition of. So it's just basically a chunk of code that you enter at the beginning. You have to go through the whole thing and leave at the end. That's it. And compilers have a lot of freedom within basic blocks because they can rearrange things and move things and eliminate things. And most things that happen inside a basic block can't be observed from the outside, right? Because you can't leave and you can't enter. So there's only a handful of things, globals, multi-threading, volatile. These are side effects that have to be still preserved inside basic blocks, but we're not going to talk much about any of those for the most part. But again, one thing to note is that when you call a function that doesn't get inlined, right, it's always the start of a new basic block. And what makes functions tricky is that, especially from the compiler's perspective, without the linker, it doesn't know all the places the function will get called from, right? So it means that functions have to be correct no matter where they're called from. I know that sounds like a really trite observation, but if you actually use that and apply it to the examples you're going to see, you'll actually get some mileage from this really trite observation. And here's a couple of examples of basic blocks. Those pictures could be bigger. So what's the first one? Can anyone just yell it out? If else, right? What's the second one? It's a loop, right? Some kind of loop. It's not a for loop, but either a do or a while. Okay, another thing to think about from the compiler's perspective is that there's two types of information when you compile a program, okay? Very basically. There's static information and dynamic information. Static is basically whatever enters at compile time, and dynamic is whatever enters at runtime. So very, very broadly speaking, this isn't literally true, but static information is reflected by types, or at least all types have to be known at compile time everywhere locally. That's the whole point of a statically typed language, right? Dynamic basically means values. Like you pass, a double, the type of the double is known everywhere in the program, but the value of the double is not. That's dynamic. So like very, very simple illustration. You've got a foo that takes a vector, okay? With a vector, the size is a runtime value, right? So if you have a loop over a vector, it's not going to know, is the loop small, is the loop big? I mean, we want compilers to optimize these things, but think about it from the compiler's perspective, right? It has no idea, typically, if you're asking for a loop over 1 million elements or a loop over 2. It has no clue. So you can start to see the constraints of the compiler, which are difficult. And the second example, of course, we pass a std array. And the std array does have the size as part of the type, right? So the compiler will know. Last slide, I just talk about this briefly. It's a bit of a toy example, but a couple years ago, Chandler Carruth gave a really good talk about fast modulus, basically, or that was part of his talk, sorry. And the idea was, well, if you add this branch into a modulus, right, you make it faster because the branch predictor is great. You know, integer division is crazy expensive, and this works out better, right? Okay. And what was interesting is at the end of the talk, he said, yeah, I should teach the compiler how to generate the branch in the assembly, even if you just do x mod m. Now, Clang still doesn't do this. I don't know the reason. But one thing I'd like to kind of throw out there is maybe this is not such a bad thing. Because, you know, is fast modulus better? Like the assembly that's equivalent to this. Is this always the assembly that we want? Well, the mean performance is better. But you don't always care about the mean. Like, for instance, what about worst case? I mean, yes, the processor is so weird that I guess it is possible that this is somehow, you know, better in the worst case. But it's very unlikely, right? I mean, you have an extra branch and then the same operation, right? So the worst case performance is almost certainly better if you don't have the branch. So there's an advantage in the compiler generating assembly that is kind of more similar in spirit to the code that you write if the compiler is not convinced that it has a good optimization to make. There's value in that because it gives you more control, right? And compilers do this often, and we will also see that in the examples. Okay, so a quick summary. So compiler has to always produce correct code. It's got to think about basic blocks and all the entry points as part of that correctness. It has a lot of some information, like types. It's got very little of other information, like values typically, or what you care about. That's one of the things the compiler really does not know in general. And it tries to make, you know, definitely better optimizations, but if it can't, if it's a judgment call, it may fall back on writing it, on generating assembly similar to the code you write. Okay, so we're going to go through basically a very large number, we're going to go through a number of examples organized in a few different sections. So we're going to be looking at a lot of C++ code and understanding why it generates some particular assembly. Okay, I'm going to start with inlining. Inlining is super duper duper important. Okay, when you first hear about inlining as an optimization, I feel like what we almost always tell people is, look, calling a function has a cost. You have to load the arguments up somewhere into some registers, and then you have to call a function pointer, and loading it up and calling the function pointer has cost. And therefore, inlining can be better. Okay, this is obviously true, right? But the real killer effect from inlining is that it makes so many other optimizations possible. When you inline a function into another, you basically fold them into the same basic block. And then what can happen is that you get all of these other nice optimizations. And my inlining example is not that interesting, but in the other examples, you'll see how inlining plays a huge role. Okay? So when does inlining happen? There's got to be two things that are satisfied, right? First, it's got to be able to. If you have, for instance, a function pointer in some totally random situation where the compiler has no additional information, it's just not possible, right? In a JITted language, a compiler could maybe decide to inline it after a certain number of calls went to the same place with like a fallback, right? But in C++, it's not possible. The second thing is that the compiler has to decide that it wants to inline. And direct calls obviously don't always get inline. And it then becomes a code bloat trade-off, right? So if you have a function that's 100 lines and you inline it 10 times, you just added 900 excess lines of assembly as opposed to it not being inlined, right? There are two cases where it's it's pretty safe to assume the compiler will inline something. Can anyone think of what those two cases are? If the function's only called once, then there's no code bloat cost. So there are still some things to consider, like if the function has to be exposed in the symbol table, like if it's not static or if it's not a lambda, it may still need to generate a body. But oftentimes, if a function is only called once, it's going to inline. You see this a lot with lambdas. And second example? Function's too small, and in particular, if the function is length 0, okay? And that's, you may laugh like, wow, why would you ever call an empty function? But you build up abstractions, and then sometimes you want no ops in certain cases, right? So you will see this. So the compiler should always, or will always really inline these things if it is capable, right? Or basically always. I should probably never say always in this talk. Okay, so here's really, really simple example of inlining. We've got foo, we've got bar calls foo, and it does not call foo in the assembly, right? This is super simple. So we can think about inlining, we can go back to our example with clear, right? So, well, what does clear look like? I mean, it basically looks something like this, right? Vector t, clear, it iterates over all the elements and destroys them, right? And then it sets n to begin. That's basically what it does. So, the type is known, right? So this call, like tilde t, t's destructor, statically, it knows exactly what it's calling. The destructor of int is a no-op, right? So when it considers int's destructor for inlining, I mean, I don't know if that literally happens, but conceptually, it obviously will say, well, inlining a no-op function is just basically doing nothing. So the for loop body becomes empty. And then it will delete the for loop, although you can't immediately delete the for loop. Even once you delete the body, what else do you have to do? What does the compiler have to prove? No side effects to what? To incrementing and equals, right? Because it's going to keep, that's part of the loop code. So in this case, like your raw implementation of vector, it's probably, well, I mean, it's not probably raw pointers. It's a pointer type def that comes from the allocator, but it's all going to be resolved, hopefully. But you can see even in this trivial case, the compiler has to eat away a lot of compile time abstraction to fully make the optimization. And this is a very simple example. But it does do it very reliably in these cases. So yes, if you look at the assembly, by the way, spoiler, yeah, it optimizes away completely. Okay, so Const Propagation is kind of, after inlining, those are maybe two of the most important canonical optimizations. So remember before I said, well, types are compile time and values are runtime, right? Okay, well, this is an exception. So basically, Const Propagation is when knowing a value at compile time influences the generated assembly of the compiler. That's at least a working definition of what it is. So it's super important as a result. So let's look at another example. This is an example of sort of arithmetic Const Propagation, you can think of it. So Matt Godbolt gave a keynote last year, I think, where he went through a lot of arithmetic optimizations. So here's one very simple example. So foo calls factorial with a constant, and one thing to note in this example, right, is notice there's a relationship with inlining. So it's not just the fact that the call to factorial is gone, but again, this will sound trite, but foo cannot call factorial and get back 24, the constant, right? Because factorial has to be correct for all values of x, right? So once you're actually entering factorial, the main factorial function, I'm not really going to talk about cloning in this talk, but there's a thing called cloning, but we're not going to talk about it. But once you enter the main factorial body, it has to be correct. So you're not going to get Const Propagation through a function boundary in most cases. And this is all based on really trite observations, but a lot of people, when looking at code, will sort of be surprised, like, oh, like, why didn't this const propagate? I mean, that's why. And by the way, notice it has nothing to do with the keyword const, right? No relationship to keyword const. But we will talk about that too. Okay, so arithmetic optimizations are nice. Depending what kind of code you write, they might be important. But I think this is, to me, a more interesting example of Const Propagation. So here I've written, sort of my own for each function. It takes a function pointer and a vector, and it just calls the function pointer on every element of the vector, right? So here we have bar. Bar calls my for each, v foo. Okay, so foo is a function that does something, right? So if you were looking at this code, maybe, and you hadn't been at this talk and thinking about these things, you would probably just think, well, I 100% expect foo to get inline because look, like bar is saying exactly what it's calling, so why wouldn't it be? But what is basically a necessary condition for foo to get inlined in the total generated assembly here? Did anyone say? Yeah, well, foo won't be eliminated, but I'm saying for it to be inlined. So, I mean, the answer is that my for each has to be inlined into bar. Because if bar calls my for each, and actually, incidentally, I started this example with standard algorithms, and to my surprise, a lot of standard algorithms do not get inlined fully, even at O2. At O3, they typically do, but you'd be surprised. So if my for each does not get inlined, right, there's no way that my for each can inline f, right? Because it has to be correct no matter who calls it and no matter what value of f is passed. So to you, it seems like I'm passing foo. Why aren't you inlining me? Well, that's why. Because you can't const propagate across this function boundary. If you inline my for each, then all the code is in one scope, right? It's one big chunk, and now the compiler can do some stuff, right? So here's the assembly. Unfortunately, it didn't entirely fit on one slide, but if you go through it, you'll see that bar neither calls my for each, nor does it call foo. It just generates a bunch of instructions, okay? Oh yeah, so for instance, std find if. That's almost probably one of the simplest algorithms you can think of. If you call it with a function pointer, for instance, GCC8 with O2 will not inline it. It will not inline find if, and then it will not inline the function pointer either. So you will actually end up with assembly significantly. You can always say maybe inlining is bad in this case because of code bloat, but in practice, you almost always want this small function inlined, right? So you will actually get worse performance with find if in this example. So, lambdas are good. Okay, passing by reference. So, notice what am I doing here? I'm passing a bool by reference. Why would I do that? Well, I don't know. Don't do that, huh? Templates, right? So when you write generic code, right? Like, your first reaction is like, oh, no one passes bool by reference. Yeah, you do. Every time you write const t ampersand and t gets reduced to bool, congrats, you passed a bool by reference, right? And this is actually, it can be a real issue in some code. So let's look at this example. So we have quux. Sorry about the function names. I'm lazy. I couldn't think of like cute examples like some speakers. Okay, so you've got quux. Quux goes in a loop. Every time through the loop, it calls bar. If b is true, it also calls this other function foo. Okay? And you have foo and bar. The compiler doesn't see their definitions, only their declarations. Great? Great. Okay. So here's the assembly. One of these is from if it's a reference. One of them is if it's by value. Can anyone guess which is which? Who thinks that the one on the call by reference, the pass by reference is the top one? Who thinks it's the bottom one? Okay, so most people aren't sure. So it's the top one. The comparison is sort of on this byte pointer in direction instead of this direct register test that you have in the bottom one. So, actually, let me take a step back. So the difference in this assembly is quite small in practical terms. But there are other optimizations that you can do that are important. So for instance, in this code, which is quite small, one thing the compiler could do is it could take the loop out of the for loop. Sorry, take the branch out of the for loop, right? So in other words, it could have the branch at the beginning, and then it could have one loop that only calls bar and one loop that calls both bar and foo. Yeah, yes. You're stealing my thunder, but yes. So, okay, so, aside from this small change in assembly, if you crank up optimization to 03, it will do this if you pass by value, but not by reference. And also more broadly, like even in that small example, you could ask, why are you doing this indirect comparison over and over? Why not copy the bool into a register, right, once, and then when the loop iterates like 1,000,000 times, you can just do the cheap register comparison, right? Right? Wrong, okay? You can't do that. So here's my bool. It's a global. Everyone's spider sense should be tingling now. Something bad is coming. So my bool is a global, and bar is flipping the global over and over and over and over. How super obnoxious is that? So when you call this for loop, you'll actually alternate between calling foo and not calling foo. Okay? So whenever you pass something by reference and you want to ask yourself, how will this optimize, you really need to assume the worst. The worst for passing by reference is basically if you pass a global, because now every single function can change it. And of course, well, here's the next one. Const doesn't matter, right? Applied to a reference, it's basically useless for optimizations. Again, basically, I'm leaving myself an escape hatch. So you can always cast away const. So if the underlying value is not const, it's defined to cast away const and modify it. And so in this example, right, like foo does not know if the original value is const or not. So foo may be written such that it modifies its argument, right? That will only be UB at runtime if it's called with a const argument. So this gets pretty nasty. So here in this example, right, you can see what I'm doing, right? So there's signed integers, x, so y is equal to x plus 1. So if y doesn't change, it's now always bigger than x, okay? The compiler is allowed to make that assumption for signed, not for unsigned. That's just throwing in their integer fun optimization. Okay, so this will not optimize, right? Because foo can change the argument, as I already told you. Sorry, let me take a step back. It will not do the optimization if the const is not applied. Now, let's say that y is actually const, okay, like in the code on the slide. Sorry about that. How many people think that it will just return true at the end? I mean, y is const, right? It's illegal to change, right? Like it's actually illegal to change y in this program. How many people think that it will still do a comparison of y and x? Okay, maybe I set you guys up for that, but really you guys should have said the first answer, right? I mean, the compiler is allowed, as far as I know, to just return true, because it really is illegal for foo to change y, but it doesn't. Constcast would be undefined behavior here, because y is actually const. So like actually changing a value that is const is UB. But casting away const for something that's not const is not. So y, the value here, is actually const. The compiler doesn't do anything with that. I mean, so there's a comp instruction there, as you can clearly see. So if you change it to pass by value, then it works. But once you change it to pass by value, you don't need the const anymore. So, so I guess different views on everything, like how const affects optimization. One person that I talked to said, well, the impact is not 0, but it rounds to 0. So that's kind of my view on it. But you can find edge cases where const makes a difference. But this is a pretty simple case, and the compiler's not doing anything. Okay, branches. So let's talk about optional. So one fun fact about optional is that the star value, the starring, like dereference optional, is not checking anything. So it's undefined behavior if it's empty. And .value does a check and a throw if it's empty, right? I've always disliked this, but I was really embarrassed to say this during my talk. But then Andre said it, so now I'm in good company, if you guys were at Andre's talk. And one of the arguments that I always heard from people that said, no, like star shouldn't do the check, like the undefined behavior is okay. They always said, look, this is the idiomatic usage, right? Well, imagine that was a star instead of a value. They say, well, imagine if you use it like this, right? Then, you have one branch in the code, and then inside the body of value or inside the body of my hypothetical star, you have another branch, right? You have to check if it's true to see whether to throw or not. 2 branches instead of 1 branch, right? Well, you guys probably know where this is going. You compile this, okay? So can all the assembly experts tell me how many branches are in this code? Just yell it. 1. Assembly experts wasn't intended sarcastically here, because you don't have to be an expert. Okay, so why? Why does this happen? Well, with our new and improved mental model of the compiler, even though it's hilariously simple, we can still explain this really easily, okay? Here's a very simple optional, probably wrong, because my reinterpret cast is probably somehow UB, I don't know. So this is the idea, right? If active, return some cast of the storage, otherwise throw, right? And there's a valid. I didn't even write it, but you guys can imagine what valid looks like, or the bool. Okay, so here's the original code. Here's what it looks like. All these functions are really short, and they're going to get inlined. And what happens? Well, if m active, I mean, if you're in the m active branch, then m active is true, right? I mean, that's pretty easy for you to figure out. It's pretty easy for a compiler to figure out, too. So the second branch just vanishes, and you just don't get any of that junk. And you saw what the assembly looks like, right? Not only is there no second branch, there's none of the exception-related junk that you might expect. So the compiler does this very, very well. So, so that is not a good reason why star should not do the check. Maybe there are better reasons. I don't know. Okay. So this section we're going to talk about a little bit about how to write code a little differently to help the compiler. Okay, so this first technique I call with bool, it's a little bit comes back to our previous example where we have a Boolean in a loop. So one thing is that compilers are not very aggressive about pulling a Boolean out of a loop, even at 03. And I actually understand where the compiler is coming from. It duplicates a lot of code, and the branch predictor is good, right? So that branch doesn't cost much necessarily. But sometimes you really know that you want to pull the branch out of the loop, despite everything. Can someone give me an example? Like, why would I know, even without measuring, that I really want to pull this branch out of the loop? There's actually one very simple example. So very simple example is basically if you know that you're only ever going to call one version ever in your program. And that may sound really weird, but this happens all the time. You have Booleans that enter at configure time. And you read it once from the configuration, you're only ever going to use that value. So it's a runtime option, but it doesn't change for the life of the program. So depending what domain you program in, you might have a lot of data like this, you might have a little. In HFT, this is super common. So if that happens, you're making your binary bigger, but that extra code is never being executed. So the iCache impact is basically 0. And it probably makes sense to pull it out. Although, you probably should measure to double check. But you need a default, let's put it this way. So how can we force the compiler to do this, even though it doesn't want to? Of course, templates. I think templates are basically there to coerce the compiler. So if you just use a template, though, you'd need to pass the bool at compile time. But we have a runtime bool. That's no problem. We do this. This pattern, I don't know if there's a name for it. I always think of it as a lift. You take a runtime value and lift it back into the type system by paying a one-time cost. So that's sort of what's going on here. And we can actually extract the generic part of this. So here's with bool. It takes a functor, and it calls it with either stood true type or stood false type, depending on the value of a runtime bool. And you can use this generic construct to rewrite quacks, and it's pretty nice, right? I mean, it looks pretty much like the original with one extra set of indentation. So yeah. So let's kind of conclude the sorting saga. So why, if we think about all the things we've talked about so far, why does this produce poor assembly? Well, it comes back to this problem. When the function pointer gets past a sort, it deduces its type. And its type is going to be a function pointer type, right? And that function pointer, the type, it does not encode what's getting called. It's the value of the function pointer that decides what's getting called. So remember, now you're going to say, well, but I'm calling sort with a constant, right? But we saw in the previous example, if sort is not inlined, and it's not going to be inlined, it's big, then you're not going to expect MyComp to be inlined into sort either, generally speaking. GCC with O3 will not inline sort, but it actually clones sort, and then you get the inlining. But it's very hard for the compiler to know whether it's worth it. And that's why doing something ridiculous like wrapping a function pointer in a lambda, it actually communicates a kind of intent to your compiler. Right? Like no compiler will ever take multiple sorts called with different lambdas and then fold them back together and add indirection. That doesn't happen. So there's like a really interesting thing you can do around this, especially in C++17. You can have this function object lifts the function pointer into a type. And there's actually a proposal for this. It's called monostate function. So this is kind of like the lambda, but with all the details taken care of for you. Okay. So this last section is called, well, it's a cry for help. So this is about code that's like hard to write efficiently as things stand. So I don't know, maybe the goal is to draw attention to it. So, the talk's originally about, me helping you, help the compiler, help you. And now I'm trying to help the committee, help you, to help the compiler, to help you. So it's all very helpful. Okay, so reading bytes destruct. So in certain industries like HFT, this pattern, you have a buffer of bytes, you have a header, you reinterpret cast to get the header at the front. The header tells you the type of the data that follows, okay? If you're in HFT, you write this code like you breathe. I mean, it's just seems totally natural. Everyone does this with reinterpret cast. Everyone. There's like one little problem with reinterpret casting here, which is it's undefined, okay? Maybe my alignment is wrong. These slides are super simplified, but even if the alignment was perfect, it would still be undefined behavior. There is no object that's ever been created as far as the compiler is concerned of header type. So this is the compliant way to do this. You header type, you memcopy. Okay, well, memcopying is doing stuff, right? Now, if you talk to people, like one of these tried generic observations that people will make that I really dislike is they'll be like, oh, but the memcopy will get optimized, right? So I hope by this point in the talk you guys are too suspicious to just accept the idea that the memcopy is going to get optimized. So here's an example I can actually feed the compiler. So header type and first type are just basic structs with a couple of int and double fields, nothing special. So I feed this in, and basically what you will see is that one of the memcopies gets eliminated, and one does not, okay? So the first part of the code, that corresponds to reading the header. There's no memcopy there. But the second part of the code, you'll see the move DQU and move APS instructions. For my small struct, that's actually what memcopy ended up being, because it was just a couple of fields. So one gets optimized, but not the other, okay? So, whoops, so why, why? The answer is basically, like, in the first case, it's only using header type locally, right? Everything's by value, everything's local, you're all in one block. The compiler can see exactly what's going on. In the second case, you're taking this object and you're passing it into a function that the compiler knows nothing about by reference. Remember how const reference is worthless? Right. So this function can cast away const and it can mutate the type. And now, suddenly, whether you memcopy it or not is a semantic difference, right? In one case, the buffer is being mutated, and in the other case, it's not. And the compiler will memcopy for that reason. So how can we fix this? So we want an object, so it's not UB, like a true object, and we want to construct it in an arbitrary point. How do we do that? Placement, no, don't do this. So this version of Safecast that just placements new an object, we should really static assert that the object is trivially everything. And this will actually work typically, but you're just banking on the fact that a placement new literally does nothing, right? Like, that's not required by the standard. It's actually unspecified what happens. Like, it's equivalent to int x and then reading, Well, it's not quite equivalent, but there's no guarantee that the underlying memory is the same. It's just unspecified. So So here's a really crazy trick I can't take credit for. Some dude on Reddit told me this. It's pretty cool. So the idea is that the placement new could actually overwrite stuff if it wanted to. So you create a buffer, you copy out where you want a placement new, then you placement new, and then you copy back. So it's like the song, like 2 memcopies are better than 1, right? Because this just optimizes to nothing. No memcopies, ever. Pretty crazy. There's a new problem that's been introduced by placement new. Can anyone tell me what it is? I introduced a new problem, right? It's like trying to cover, a large animal with a very small piece of cloth, like you shift it around and a different part of the animal's not covered, right? What's the new problem? What's that? No. The new problem is that it's not const correct, okay? I mean, to placement new, you need mutable access. And conceptually, we are not writing to the buffer. Why should we need mutable access to this buffer? This is nonsense. So you could const cast, see the dark road we're going down, but I guarantee you in a large enough program, if you cast away const, someone will eventually pass in something const, and you will segfault. So should you do that? Should you reinterpret cast? All the options here are terrible. I don't know what to tell you. 3 months ago, I would have said just reinterpret cast. And I thought there was like a gentleman's agreement that compilers would not optimize based on that UB because there's no other good way to do it. But now it seems like they are. I had a crazy bug with GCC at 03 where it just turned a perfect, like a function that used reinterpret cast into garbage. And it took a long time to track down because like adding a print statement would change all the code gen and make the bug go away. So that's super fun to debug. Okay, so my last example, I'm going to grind through this really quick. So this is related to the first example a little bit. So you have the situation where you have a runtime variable telling you how to understand a certain piece of memory, right? And maybe you want to apply some function that depends on the type. So here we have a visitor, we have a runtime index, and we're calling different functions. This is great, right? There's one problem with this code. It can't be made generic, right? Like switch cases cannot be generated. So how do we do this generically? Well, you can use function pointers. So this is my really bad approximation of template magic stuff. But the basic gist of it is you create a function pointer that takes the data buffer and the visitor. It casts it to the particular type, and then it applies the visitor. And then you can write a generic foo with whatever types you want, and it generates this array of function pointers at compile time, right? Const expr. And then it calls the right function pointer based on the index. Super duper awesome. Okay, this is really weird code. Why am I talking about this? If you're a library implementer, don't answer. Why am I talking about this example? Anyone know? Okay, this is how very, 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 very roughly, please don't kill me, this is how variant and visit are implemented, okay? If you've ever wondered by what dark magic you can call visit on a variant, right? And this is exactly what visit does, right? It's got some memory. It's one of a list of types based on some runtime variable. And it will call the right function in your visitor. And this is basically how it works. Great. There's only one problem. So this is some code, standard library code that you could run today with multiple compilers. What do you guys think this generates? Right? The compiler's smart, right? It is, but this code is probably not everything you would hope for. This is really bad. I mean, remember my story at the beginning? Those of you who didn't put up your hand when I asked you if you'd seen crappy assembly? Now you have. This is a no-op visitor. So this function does nothing, ever. Like guaranteed to do nothing. Why doesn't it get optimized? I have no idea. You can optimize it. You can actually write your own visit function for, it's very straightforward for the single variant case. You do have to cover by hand the different airiness of the variant. So you have to do one type vector variant and a two type variant. But you can do it, and you can do it with switch case. And write it up by hand, and you could wrap visit in your own visit, right, that calls out to the other visit if you're not handling that case. And if you, whoops, did I lose a slide? Oh, okay. Anyway, so if you change the visit from the standard visit to this visit here, you will actually get no assembly, right? And aside from the fact that, like, I'm sure all the details and const correctness and forwarding, everything is wrong with this snippet, but if you fixed all that up, you could write a visitor for 2 type variants, and it would be correct all the time, and it would give you better assembly. So the state of affairs for variant, it's not great. Personally, I wouldn't use visit in performance critical code, just right off the bat because of these issues. But you might want to consider, if you do that, write your own visit. And hopefully at some point, I mean, the compiler should be able to optimize this, so I can see the perspective that the implementation is fine. Because all the function pointers are const expert, right? So the compiler should know them at compile time. But it just doesn't inline them, and that's why you have this problem. OK, so please try to avoid generalizations. The compiler's smart, the compiler's dumb. Like, the compiler doesn't have an IQ. It's not a person. It's great at some things. It's bad at others. It's a tool, OK? It's usually very, very good within its domain when it has the information that it needs. But it also has blind spots, right? Like I saw on the previous slide. So you'll pick up what those are via experience. Understand when you can change the way you write code to help the compiler generate the assembly that you want. And I mean, I just want to close off by going back to my story. So you may have thought that my son was like 10 from the story, but actually he was 2, and he was potty training. So I mean, it was totally my fault. I should have put him in a diaper for the flight. So I had to take responsibility for that. And when you look at assembly and you feel like it's crap, then take responsibility for your crap. Thank you. Questions? Do you want to just use the mic so people can hear you? I don't know. Oh, I don't know why I'm leaning into that microphone. It's pretty dumb.
I have a question.
Oh, sorry.
Question/comment. I also work in trading.
Cool.
And I also reinterpret cast.
Yeah.
I gave a lightning talk years ago about how nasty it is. That MemCopy thing is really interesting. I'm hoping maybe possibly that the bitcast that is being proposed might be not 100% there right now, but like the right customization point to make that just be better. I had in my mind alias cast, but bitcast maybe will do it.
Yeah, I totally forgot. There's a proposal called implicit instantiation of low-level objects for byte manipulation or something like that. And I didn't read all of it, but it introduces this thing called bless, where I think you can like bless an object into existence. Are you involved with that paper?
No, but it sounds awesome.
Yeah, it's really cool, and actually, yeah, like let's move that along so all the horrors from that part of the presentation can die.
One would think that the people over in SG14 would be talking about it.
Yeah, I'm sure they are, but it's a lot of work to move anything through, right? So, but hopefully we'll have it soon. It seems to have picked up some
Great
momentum.
talk, thank you.
Oh, thanks. Yep.
Yes, so you'd mentioned the importance of knowing whether a particular function will have been inlined. So apart from looking at, obviously, the assembly, do you have any suggestions for knowing that?
I mean, the assembly is sorry, the question was like, how do you definitively know if a function was inlined? Aside from the assembly. I mean, the assembly is only the only way to know for sure, right? I mean, the assembly is what's executed. So the assembly is definitive, and other than that, I mean, you have these heuristics. I don't know of, like, if there's a way, I mean, you can use attribute inline if you know you want to force it, but I don't know a way to, like, maybe LLVM, well, that's mostly, yeah. I don't know a way to, like, log whether a function was inlined or not, if that's what you're asking.
Thank you.
Yeah. Question over here?
I have some comments about the talk, no questions. I'm not so high qualified compiler guy, but I have some vision and know something about source internal details.
Okay.
So it's first about inlining and differences between compilers. There is no very simple source of the differences because different compilers have different inlining mechanism inside and they have a lot of differences between thresholds for inlining.
Okay.
So if you look into Clang or GCC, you will find a lot of different magic numbers for different cost models. And in inlining, you can for better inlining, you can use LTO.
Yeah, I mean, so like I mentioned, LTO is like a whole kettle of fish. It can help you with inlining. I mean, my main observation is, you know, potentially one of the issues with LTO is that like inlining is not like the end game optimization, right? Inlining could be the start of many more. And at least based on my understanding of LTO is like because linking is not parallelizable, I don't, as far as I know, it's not able to spend as long grinding through. So I think LTO is like amazing, and if you just want to make your application faster in general, of course it's something you should do. But like for us in HFT, like usually it's much more like black and white. Like either I want the compiler to know about this function and definitely like optimize it, or I don't care. And if you're working in that kind of world, LTO is much less, I think it's much less valuable because I'm either defining a function in a header file or I don't care. That's like very simple for me, right?
And about your last example with stud variant, it's a known bug in GCC at least, and Anthony Paluchin already reported about it.
Oh, like this was reported as a performance bug?
Yep.
Okay, well Clang does the same thing, both with GCC and with its own standard library. Yeah, I mean the thing to keep in mind, yeah, the compiler should probably optimize that, but at some level I do still wish that like an optimization for the common cases had been written. But on the flip side, I know the library maintainers are crazy busy. One thing to keep in mind is like the average person in this room is probably on what, GCC 6, maybe? So we're on GCC 8 now. And so like if this landed tomorrow, then most people in this room would still not be getting great assembly from variant for like 2 years. So, you know, so I think, you know, my advice of maybe consider writing your own visit, you know, 2 years is like pretty good half-life for that suggestion, right? But it's good to know that it's been reported and it's being taken seriously. So thank you.
Thank you.
Oh. Yes?
Just a small question. You mentioned that Lambda gets inline better than the other option in that sort example.
Yes.
Do you know if it matters if you give it a name?
If you just like do auto x equals lambda and then you pass in x, I'd have to look, but based on what I said in this talk, I would say that it's almost certainly going to not make a difference. Yeah. The compiler actually doesn't really necessarily care that much if you assign intermediate variables. Like, I think, like, right, the earliest optimization myth that you have to dispel for people learning C++ is that, like, if they put an intermediate calculation in a variable and give it a name, they think it'll make things slower, right? Like, auto, you know, s equals x plus y, and then, you know, return s plus z. They think that's slower than x plus y plus z, and it's obviously not. With a lambda, I mean, you make the local variable right there. You pass it into the function right there in the same scope. I mean, I don't think it's going to make a difference. But if you create it like as a global lambda, right, then maybe things will be different because it could get used more than once. You know, who knows?
That's what I thought. Thank you.
No problem. Yes?
So you can have more control over compiler with like built-in attributes and like things like built-in assume.
Mm-hmm. Yes.
How much does it get in your code base? And
it gets used a lot. I'll give like one of the most canonical examples. And also I get to rant about something that I don't like. So unlikely and likely, they're actually supposed to be standardized now for 20, I think. And one thing that makes HFT tricky is that, you know, we have code paths which we really care about but are almost never entered. Because when you're trading on an exchange, you have millions of events and you don't trade 99.9% of the time. But nobody cares how fast you don't trade. So any branch predictor, right, left to its own devices will say, oh, I'm going to make your program run faster by always assuming that you don't trade, and now trading is slow. So this is the opposite of what you want. So typically what you would do is, and here's why I hate the names, you would take the likely attribute, and you would put it on the really unlikely branch, and take the unlikely attribute and put it on the really likely branch. So, so the likely attribute kind of means, compiler, please pretend this is likely even if you don't think it is. A better name, I think, would be like prioritize, deprioritize, or something like that. But yeah, that would be one example. I mean, one thing that someone from our company looked at, which I think is kind of funny, is just you have a branch on any arbitrary condition, and then inside the branch you put assume unreachable. And now the compiler will just be allowed to assume that that thing is not true. And he actually found examples where the compiler leveraged that information to produce better code. It's kind of crazy and also dangerous, because if you violate the assumption, then it's just pure UB. But you see that actually a lot at the end of switch cases, right? If you have a switch case, it's pretty common. Like if, let's say, you have return, 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 then technically you're hitting the end of a function body without a return after the switch case. It's common to put like built-in unreachable there.
Especially on like switch cases on enums.
Yeah, very common usage. Yeah.
Thank you.
No problem. Thanks. Yep.
So suppose that you take a function, you run the CPU processor, you see it's in line, you take another function, do the same, you see what is being produced in line, and you think you're going to be very smart, take all these pieces of code and try to inline yourself. And at some point you start getting functions that are bigger and bigger, and you think that the compiler should be able to do a great job. At which point this is counterproducing, and the compiler will stop giving on optimizations, according to your experience?
I mean, I don't typically advocate doing, like, in none of what I wrote here did I really suggest, like, you should just assume you know better than the compiler from the get-go. Like, I don't use force inline very often. You should probably very rarely use it without measuring, unless, like, again, you have some kind of knowledge about prioritization. I would say in general, like, write the code in a way that the compiler has the option to inline, which in many of these cases, like, it doesn't or it barely does. But let the compiler make most of the inlining decisions on its own. I've personally only seen 2 examples where people inlined or otherwise bloated code so much that it hurt performance. And both examples were very extreme. One person was just going crazy with templates, and the second was doing literal code gen, like printing C++ code that then got recompiled. Like they were unrolling loops with like 1,000 elements. So that's my experience. A lot of other people will say, yeah, like code bloat hurts performance all the time. I mean, I think it's kind of unlikely, but I also don't recommend just sprinkling force inline. Like that's not a good idea.
Yeah, but in general, do you think functions that are really, really long tend to be non-optimizable?
What do you mean by non-optimizable?
Well, in the sense that if the compiler, if you write a function, you try to boil inline yourself, you write a function that is many lines, say, I don't know, 400 or 500 lines of a single function, would the compiler give up on optimizing?
I mean, I don't know. I have to see the specific case. I mean, when you have a 400 or 500 line function, I mean, there's already a lot of basic block in there. There's already a lot of scope for optimization. So, you know, the benefits tend to be less. I mean, that's, you know, it's generally better to inline smaller functions than bigger ones. But, you know, it's really hard for me to answer your question in generality. I think at that point it all depends on, that's the point where I would say you just have to measure. I mean, it's hard to answer that question.